Okay guys, A is the number 2.718 and lots of other decimals after it. What A is used to do is to model population growths and stuff like exponential decay. Alright, now let me show you how it does this. If I have e to the power of x, okay, and what I do is I make a graph or table of e to the x. So right now I'm going to make e to the x here, so shift so e to the x, okay, and then let's say I go from, I don't know, minus 10 to plus 10, okay, steps of 1. Now look what happens to the numbers. You start off really small, so these numbers here actually, although it says 4.5, 1.2, they're actually scientific notation. They're actually really small numbers, very close to 0. So once we find a number that actually obeys this, there it is. The first one that will work is minus 4. So any of these numbers from minus 10 to minus 4 are really close to 0. And what this is representing is this part here, where it gets really close to 0. You notice it will never ever cross the x-axis. Then as the power increases, what happens to the y value? The y value starts shooting upwards. And you can see that the gaps are getting bigger and bigger and bigger and bigger and bigger. So you can see that it's just going to go up and it's going to shoot up this way, curving back inwards. Is everybody okay with that? Now, this will work for any value. I can put any value in front of e to the x. I can put 3 e to the x, 10 e to the x, and this trend will also be observed. So for example, let's go again, same graph roughly. So put a 10 in front of it, and what you're going to see is the exact same thing. You're going to see that these numbers, once again, extremely close to 0, and then it's minus 6 is the first one that we can actually see without scientific notation. 0.02, once again, following the exact same trend, and then eventually start shooting upwards, and then as you can see, big distances between the gaps. 73 to 200, 200 to 545, 545 to 1484. We can see that the graph is really getting steeper and steeper and steeper. This will obey. This is the general gist of all e to the positive power graphs. Okay? Next thing you got to worry about is what happens if it's a negative power. Well, if it's a negative power, you're going to start off with a big number, and then as x gets bigger, you're going to decrease all the way down to the x-axis. So let's have another look at this, okay? So this time, instead of having e to the x, I'm now going to have e to the minus x. Once again, put in your numbers, and look what happens. We start off on 22,000, and then all of a sudden, we're getting a rapid decline in our values. And then once again, you're going to keep going. And what are we not allowed to cross? We're not allowed to cross the x-axis because these numbers then become really small. Okay. So I was asked the question there. Well, that's great for e to the x and e to the minus x. But would any other number not follow the same trend? So let's just examine e to the x, for example. Okay. Well, if I said instead of using e, if I used, let's say, 3 to the x, okay? So 3 to the power of x, okay? And I did a very similar graph. You'll actually see that it follows the same trend. These are all negative, that's, sorry, 0, 0, 0, all the way down to 4, which is the first 0.01, and then it goes upwards. Mimics the E pattern that we've seen before it. However, if I put in a fraction this time, instead of 3, if I was to put in 0.3, which is a fraction 3 over 10, look what happens this time. What happens this time is it starts off really big and then it goes really small. So it shows you the presence of a fraction completely changes the shape of the graph. So once again, your answer is provided it's a whole number bigger than 1. It'll mimic e, because e is a whole number bigger than 1. Alright, moving on. Okay. Yes? Some people were just after asking me, why does, for example, I'm trying to think of an example here, why does f of x by, let me see, 3 to the power of x is one of these ones that starts off really small and goes upwards. Yet 3 to the minus x, how does that go? Starts off big and goes downwards. Well, and some people then ask me, what about third to the power of x? Well, a third to the power of x also follows this graph downwards. Okay, now let me explain why, Adam. See this 3 to the minus x? I can break that up into 3 to the minus 1 to the power of x. And what is 3 to the minus 1? A third. So it's actually the same thing as the fraction to the power of x. That's why they both have the same shaped graph. Is that alright? Now, what we're going to do next is revise exactly what logs are. Okay? And what exactly e to the x is. So, quick revision of what logarithms actually are. So, this is a general rule for logs. So, for example, log to the base 10 of 100. Okay? What this means is it equals 2 according to the calculator. Now what this will always mean is whatever's in the green box, whatever's in the red box, whatever is in the blue box. What's always going to happen is blue box will equal green box to the power of red box. Always. So for example, 100 will equal 10 to the power of 2. Another example would be log 10 to the base 10 is 1, in which case 10 equals 10 to the power of 1. That's the rules it will always obey. Please make sure you remember. Now that we've sorted that out, what we got to understand next is that logs are actually inverses. Log and e to the x are actually inverses of each other. So let me explain why. ln means log to the base e. ln 5 would mean ln. ln 5 would mean ln log to the base e of 5. Okay? Now let me explain what happens when you get e to the x. Okay? ln e to the x. Okay? ln e to the x is basically log e to the x. Now what did we say about powers and logs? What can we do with the power? It's not the first time you've seen this recently. Up to the front. So it's going to be x log base e to the base e. Now what do we know about logs? Any log to the same base? 1. So this means it's going to be x times 1, which is x. You happy with that? So basically ln e on its own is 1, always 1, because it represents log e to the base e. Now, that explains the one to the right. But what about the one to the left? Well, the one to the left basically means that if I had e to the power of anything, okay? So e to the power of ln x equals x. Okay? What I would do, anytime you have the variable in the power position, do you know what you have to do to get rid of the variable? Does anybody remember? What do you have to do to get rid of the variable in the power position? You got it, but you can only do that when you log both sides. Now once you've logged both sides, you can bring ln x to the front. It's going to be ln x ln e. And what do we know about ln e?
1.
Sorry? 1. And then therefore we have ln x equals ln x. Both sides are balanced, hence proving that it's an inverse of each other. Okay? You might want to do that out another time, once or twice yourselves, just to make sure that you understand the movements involved from both scenarios. Okay? Now that that's done, once again we're just after agreeing that these two are inverses of each other, correct? And what happens when you draw inverses of each other on a graph? They're mirror images of each other in the line y equals x. We would have learnt that yesterday, okay? So for example, if 0, 1 is a point on y equals e to the x, what must be a point on its inverse? 1, 0. So you can see that you're exchanging the y values for the x values in both graphs, okay? And there you go. Now, asymptotes. This is what Kim was asking me the other day. What we know is about e to the x. What line is e to the x not allowed to cross? It's not the y-axis, it's going to be the x-axis. And it goes all the way across, never crossing it, but getting closer and closer and closer till it's practically, to your eyesight, it's practically on the line. Okay? Now what about the asymptote for ln x? And the y-axis is a vertical line, which makes it the vertical asymptote of ln x. Isn't it funny that one of them has a horizontal asymptote, which is the x-axis, and then the other one switches to the y-axis. Once again, y being changed with x, because they're inverses of each other. Okay? Now, what we're going to do next is, what we're going to do next is questions 1 and 2 are just using your calculator. Here's ones we need to practice, okay? Now, simplify each of the following. Okay, so simplifying. Only thing you need to know about this is that powers, okay. Ready, guys? What you need to remember is E, ln x, they're inverses of each other. The E and the ln. So E in the base position, ln in the power position, they're inverse functions. And what they do is they cancel each other out, leaving the answer as x. So the E and the ln cancel each other out, and the answer is x plus 2. Likewise, in this one here, the E and the ln cancel each other out, and what's the answer? X squared. That will always happen. Now what about this one here? We can do the power rule, can't we, for number 2? What's the power rule? 5x minus 1 ln e. Ln e turns to? The answer therefore? 5x minus 1. What about this one here? Square root to the front, ln e. The answer is root x. Okay, moving on. Solve these, correct the 3 significant figures. So what I'm going to do is I'm going to start off with number 3, because number 3 is a hard one. Okay, so number 3 we have 2 e to the x minus 1 equals 81. Bring the 1 over to your side. 2 e to the x equals 80. E to the x now equals 40. Can everybody understand that question 3 is now exactly the same as questions 1 and 2? So the same method will apply for all 3. So what I'm going to do next is I'm going to ln both sides. And that is the only way you can get rid of the power of x. And the x goes to the front, becomes x ln e. And what's x ln e again? Plus x. So x equals ln 40. And then we're also asked that ln 40 be given to 3 significant figures. Now don't be kidded by significant figures. Okay, I'll give you an example. 4,200 is 2 significant figures. 42,000, 2 significant figures. Okay, it's the numbers that aren't zeros. Okay, however, 40,200, 3 significant figures, because this 0 is located in between the 4 and the 2. Zeros count if they're located in between the 4 and if they're located in between 2 numbers. Another example would be this, guys. This one here, 0.0019. How many significant figures here? 2. What about this one here? 3. What about this one here? 1, 2, 3, 4, 5. Technically 5 because the zeros are locked in between 2 different numbers.
So what would you name?
Okay, so lads, what happens here is we're looking at ln 40. ln 40, therefore it's going to be, what's ln 40? ln 40 is 3.68. The 3 is a significant number. And the 68 is 2, that makes 3, but we should round it up to 3.69 for 3 significant figures. And in this case, it's the same as 2 decimal places. But significant figures aren't always the same as decimal placing. Okay, so now we've done that. What we could do next is the example. For example, number 6. Once again, very similar to some of the other ones here. We're going to move over to 4, and we're going to get e to the minus 5x equals 1. We're going to ln both sides. And then what we're going to get is minus 5x ln e equals ln 1. I have a sneaking suspicion ln 1 is 0. ln 1 is 0. So what we're going to get is 0 equals minus 5x. Therefore x has to be 0. Now that that's done. Finally, last type of question here. Last type of question is solving logs. ln 4x, move over to 4. Move over to 1 and becomes a 4. ln 4x equals 4. Write down what ln actually means. ln means log to the base e. And as discussed earlier, if you forget this in the test, there's a way of rejogging your memory. Basic way I always rejog my memory is I always do 100. I put that into my calculator and I get 2. And then I have to figure out which movement makes it equal. That's going to be 100 equals 10 to the power of 2. So I'm going to do the same movement here. I'm going to bring e to the power of 4 equals 4x. X therefore equals a quarter e to the 4. And then what I can do there is a quarter e to the 4 on the calculator and find out what that is. Okay, so that is going to be e to the power of 4 and 13 points. Now 3 significant figures means that I have to round that off. See the 6, 4, 9? That can catch you out. Because you round off to 6, 5, then you round up to 7. But it should be 13.6. Okay guys, that's question 4 done. Now, question 6. A species of has an animal population growth modeled by p of t equals 10 minus 5 e to the minus t. Now, this is what type of graph on its own? What happens to this number? Does it get bigger or smaller as it gets smaller? So let's find out on its own, alright? So look, the great thing is you guys have the ability to, you don't even have to predict stuff anymore. You can just put it into the calculator and just do a quick experiment to see what actually happens.
Did you ever have to predict it then?
Yeah. So we would have to be minus 4, let's say, to plus 5, gap of 1. Now let's see what happens to 5 e to the t. Starts off big, it then gets smaller. Okay? Now, this number is going to start off big and it's going to get smaller and smaller and smaller. Now, it's going to eventually get so small that it's going to be like taking away nothing. Do you understand? So, what happens at the start is 10 is getting subtracted by a reasonably big number. So 10 is affected, it ends up much smaller than 10. But as the t number gets bigger, this number here practically becomes 0. So I'm expecting the last number to be very close to 10. And what happens as I go all the way up to, let's say, 100? It will just tend towards 10. So the graph will be capped off at 10 on the y-axis. So let's see if this is what happens. So just for the sake of completeness, okay, what we're going to do here is we're going to just do 10 minus 5 and then shift e to the minus x. Okay, look what happens here. Start at 0. I'm going to end it at 10. I'm going to end it much higher than I meant it. And look what happens. Okay, so what we get for the first one is 5. 8.16. So if somebody could have that up, that'd be great as well. 8.16. The next one after that is 9.32. After that, we can see it's going to be 9.75. After 9.75, we're going to have 9.9 and 9.91, 9.97. Is it 9.91? 9.97 is correct. And then what happens further up, guys? Look what happens further up. It's getting ridiculously close to 10, but it's never going to reach it. Okay? So, Copy and complete the table given P and T correct to one decimal place where necessary. I was meant to do that to one decimal place, so technically 8.2, 9.3, 9.8, 9.9, and the other one will be 10. Find the size. What happens to the size of the population as time goes on? What did we say happens? It's going to practically become 10. As t goes to infinity, do you understand what I mean by t going to infinity?
Very, very well.
As you go longer and longer and longer, p of t will turn to 10. Because it's going to be like 9.99999999999, and that's so close to 10, it's practically 10. Okay, number 7. Graph this function from 0 less than or equal to 3. So once again, you just use your calculator, quickly does it. You do 2 plus 6 e to the minus x. I often do more than I have to, just because I like to have more information. Okay, and we can see that it's decreasing from 8 down to 2.2. Now, what you're going to be asked to do is that this graph here is a decay function. It's getting smaller over time. Now, it goes, graph this function, it's done. Use the graph to verify an approximate solution for this here. What is an approximate solution, guys? What does this part here represent on its own? The part I underlined in red represents f of x. F of x equals 5. That's the same question as asking y equals 5. Go up to y equals 5, draw the cross, hits the line, goes down. What do you think our answer is going to be? I say roughly 0.7, isn't it? 0.7. Part 3, verify your answer. Bring the 2 over the other side. We're going to get 6 e to the minus x equals 3. E to the minus x will equal a half when we divide by 6. ln both sides. ln e to the minus x equals ln a half. Okay. Minus x ln e equals minus x. Now, there's a rule for fractions. Remember this? ln a over b equals ln a minus ln b. This is going to be ln 1 minus ln 2. What is ln 1? 0. Minus x equals minus ln 2. X therefore equals ln 2. ln 2 should be a number very close to 0.7. Is that the case? Can somebody find ln 2 on the calculator? 0.69. Couldn't have been any closer if we tried. Or it could have been slightly closer, but you get the gist. Okay? Now, everybody happy with that? Okay. I corrected 2 decimal places, so technically just always reread the question. 0.69. I got 0.7. When I did it algebraically, it's 0.69. Which one's the more accurate answer? The 0.7 or the 0.69? Algebra always beats graph for accuracy, because graph is open to interpretation error and scaling error. You'd be asked that in tests at times. Okay? Now, these ones here, inverse functions, guys. Now, I'll do 2 of these for you, because the other 2 are exactly the same. I'll do the harder 2. This one here, and this one here. Okay? So what happens here, guys, is the following. We replace f of x with what? Y. Do you remember when we're getting inverse functions? Step 1, get x on its own. The 3 has to go first. And now we have x, e to the x minus 1. Don't change that around, because in general, I like it on the left hand side. Okay? So guys, what's the rule for isolating the x? Where's the location of the x at this point in time?
Power position.
Power position. What does that mean about both sides? What do I have to do?
ln.
ln both sides. Bring the x minus 1 to the front. X minus 1 ln e. What is ln e? 0. Oh, sorry, 1. ln e is 1. Means we don't have to put it in. And now we're going to get ln y. Now, this ln is ln y minus 3 in brackets. ln y followed by minus 3 is 2 separate numbers. However, ln bracket y minus 3 is considered to be one number. Please make sure of your bracketing in these questions. Next part, guys. We got to isolate x. So it's going to be, we're going to bring over the 1 to the other side, and we're going to get x equals 1 minus ln y minus 3. Oh, sorry, plus. What's our last step then? Change x into f inverse x and change y into x. And that's it. Part 1 follows the same pattern, except it's an easier question. Okay? Now, what about this question here? One that has an ln instead of an e. Let's follow the same procedure. Y equals ln x plus 2 minus 5. Bring the 5 over the other side. 5 plus y equals ln x plus 2. Switch. ln x plus 2 equals 5 plus y. Now, what does ln mean again? ln means log to the base e. And what we know about this is that this means that the x plus 2 equals the base number to the power of the other number. And then we know that x on its own is going to be e to the power of 5 plus y minus 2. Everybody alright with that? Any questions? It's number 10. F of x equals ln x minus 1. X greater than 1. Why does x have to be greater than 1? You can't get a negative log. So ln of any minus number doesn't exist. So for example, ln minus 3 doesn't exist. Maths error. Okay? Now, let's begin. Let's find f inverse. Y equals ln x minus 1. ln x minus 1. Yes, Shane? ln x minus 1 equals y. Log to the base e, x minus 1 equals y. X minus 1 equals e to the power of y. X equals e to the power of y plus 1. Change x with f inverse x. Change y with x. And there's your function. There's the reverse function. Okay? Now, upon getting this, it wants me to find out what f inverse 0 is. What do you mean by f inverse 0? Replace x with
0.
E to the power 0? 1 plus 1? 2. Okay, not so bad. Next part after that. Now I'm just going to rub out all this part here. Okay, and what we're going to do is just take the answer. Okay, which is here, all the way up to the top. Now, it wants me to do g after f of 3. So what I need to do is f of 3 first. And what's f of 3? E to the power 3 plus 1. I'm not going to put that into a decimal or anything like that. I'm going to leave it as e to the power 3. Now it wants me to use the g function on it. So the g function is, what's the g function? E. So g of x, g of the box equals e to the power of 2 times whatever is in the box. As it turns out, it was x at the start, but now it's going to be e3 plus 1. So let's find this out. It's going to be e to the power of 2 times e3 plus 1, which is going to be e to the power of 2e3 plus 2. I'd leave the answer like that because it doesn't say anything about decimal places. However, maybe in a test, do you know what? I'd hedge my bets and do both. And what I do is 2, shift to the 3. You can see it here. And then we shift that over to plus 2. And then I get, do you know what this is, guys? It's a really, really big number. It's 2.06 by 10 to the 18. So, which is a very big number. Okay, because it has going to have 18 zeros. Okay, and that's expected. A big massive power. Alright guys, shh. Next one after that. G after f of x. Shh. So, g after f of x, okay? So what g after f of x would mean is something similar to what I just did. It's going to be g of whatever is in the box. It's going to be g of e to the x plus 1. And that means e to the power of 2, whatever's in the box is ex plus 1. Multiply it out. E to the power of 2, e to the x plus 2. As I said, remember, it's g of whatever is in the box. So we did the first function first. Replace f of x with e to the power of ex plus 1. And then what we did there was we then put that into the g of x function. Alright guys, number 12. The graphs of the functions f of x equals e to the 2x plus 1 and g of x equals 5 meets at h5. Find h exactly. H is 5 the input or the output function? It's the output. And what's the output? F of x. 5 equals e to the 2x plus 1. Bring the 1 over to your side. 4 equals e to the 2x. How do you get rid of x in the power position? ln both sides. And now we're going to get 2x ln e. And what's ln e? 1. 2x equals ln 4. Therefore, now, if you look at the back of the book, okay, it's going to be ln 4 over 2 equals x. A lot of people would leave the answer like that, which is fair enough. The answer in the back of the book is ln 2. Can anybody figure out how to change ln 4 over 2 into ln 2? It is. You can't divide by 2 because it's a function, it doesn't work regularly. So, Connor, these two numbers, it usually doesn't work regularly. So, let me give you an example. ln 6 divided by 2 under that logic should be ln 3. Let's check it out. So what you do is you check two different numbers, okay? So this one here is going to be ln 6, which is 1.79, divided by 2 is 0.896. Now let's check out what ln 3 is. And if ln 3 matches up, then you can do what you're talking about. Does ln 3 match up? It doesn't. So we're not allowed to do that. Okay? Now, can anybody suggest another way around this? What is 4? 4 is 2 ln 2 squared over 2. What can I do with the power? 2 ln 2 divided by 2 cancels, gets you ln 2. It was just a coincidence that it divided in that way.
So you can divide the 2 that's on the outside.
Yes, but not the 2 that's on the inside, because the 2 that's on the inside belongs to the function, and it no longer represents 2. It represents something else. Okay? So, next part, guys, okay, is a function is defined by 2 e to the minus x minus 1. A sketch is drawn. Find the value of a. What's the input at this point? Input is 0. Output is a. Long story short, f of x is a, and input is 0. And what do we get here, guys? A equals, what's 2 times e to the 0? 2. 2 minus 1? 1. A equals 1. Show that b equals ln 2. Is b an input or an output? B is an input. And the output is? So replace f of x with 0. 0 equals e to the 2x plus 1. Bring the 1 the other side. Oh, sorry. Thank you. 0 equals e to the minus x minus 1. Bring it over to the other side. We're going to get 2 e to the minus x equals 1. I brought it to the other side and then followed up with a switch. Okay, and then we're going to ln both. Half it first if you want. Then we're going to ln both sides. Then upon ln both sides, we're going to bring the minus x to the front. Minus x ln e equals. Now what is ln a half? It's ln 1 minus ln 2. minus x equals minus ln 2. Multiply both sides by minus. X equals ln 2. Everybody know that's the fraction rule for logs, yeah?
I don't see how you made the... Oh yeah, no.
Now guys, a question was, for this question was, why at the start we had e to the minus x, okay? And what we said was that it couldn't cross the x-axis. Now the reason why it's allowed to cross the x-axis is, see this minus 1. This minus 1 is basically shifting the full function down in 1. So for example, if I was to do this, it looks something like that, and it never ever crossed the x-axis. This minus 1 drags it down, so it crosses through the x-axis. Okay? So that's why that can happen. What is the range of f of x? What is the range of the function? Now what does the range of the function mean, guys? The range of the function means the y values. What is the lowest y value you can think of? Well, look at this. F of x equals 2e to the minus x minus 1. Now what happens to e to the minus x as it gets really big? Let's find out. Okay, so we're going to do a table. And what we can do here is e to the minus x on its own. Now look what happens when e to the minus x becomes really, really big. When the x values become really, really big. Start at minus 10. Finish at 10. Step of 1. Look what happens. It starts off huge. Starts off all the way up here, and then what happens? Becomes really, really, and what's happening to the values? Getting closer and closer to 0. So in effect, this value here is going to become 0 as x gets bigger. This means the function, the value is going to be minus 1. Let me show you this on graph. Okay, if we were to draw out this function, okay, can somebody call me out the equation, please?
2e to the minus x minus 1.
Sorry, so y equals 2e to the power of minus x,
Minus 1.
then minus 1 after that. Oh wait, I probably should put that in brackets. So 2.
Yeah, 2e to the power of minus x.
Sorry, in seconds. So 2e to the minus x, to the power of minus x, and then after that?
Minus 1.
There it is there. Now guys, what we can see, for all intents and purposes, what happens at minus 1? It just starts going horizontal. So you can look at the graph from two different perspectives. If I make the graph flatter, look what happens, go straight across. If I make the graph more detailed, we can see that it bends downwards, and then all of a sudden it starts going flat with minus 1. This line here, although it looks like it's on minus 1, if I was to grab the axis and make it much more refined, look what happens. You can actually see the gap for a bit longer. Okay, but it isn't at minus 1, but it's very, very close to minus 1. Okay guys, finally, so the range is going to be, your bottom is minus 1. So all your y values are all going to be bigger than minus 1. Solve this equation equal to 3. When you solve this equation equal to 3, what we're going to get is 2e to the minus x minus 1 equals 3. Bring over the 1 equals 4. 2e to the x equals 4. Divide by 2. E to the minus x equals 2. ln both sides. And upon ln on both sides, what we're going to find out is that ln minus x ln e equals ln 2. Minus x equals ln 2. X equals minus ln 2. And what we got earlier was that ln 2 was 0.69. So it's going to be minus 0.69. Now, we could also do this graphically. Solve f of x equals 3. Solve the y value equal to 3. Look what happens when I go back to my graph here. Y value equal to 3. Now I'm just going to drag this down a little bit. It's equal to 3 here, isn't it? And if I drag this out a bit more, 3. And 3 occurs when I go all the way down, it's going to be roughly 0.7. So the graph backs up my algebra. Okay, 14. This one is a really weird question, but it's actually not that difficult at all. In fact, it's the easiest question in the full thing. It goes, Benford's law states that for a set of numerical data, the properties of the number starting with the digit d, approximately modeled by p of d equals log 10, 1 plus 1 over d, show that Benford's law predicts that around 30% of numbers start with 1. So I found this question really hard last night, but then what I did was I risked my arm at it. I didn't know how to do it, so I risked my arm at putting in the function. Okay, so this is what I did, and upon putting in the function, just to make an effort at it, what I found out was, oh, it's automatic.
You have no base 10.
When you have log, you could put base 10, but when log on its own is always base 10, unless you specify a different base. Now I'm going to start at 0 and end at 10, step of 1. Now look what happens. 30% start with 1. Do you see this here? 0.301 represents 30%. What about this one here? 2 represents 17.6, which is 18. What proportion of numbers does predict starts with 9? And look what happens when it starts with 9. 0.0457, which is roughly 5%, rounded up. Now guys, you might be asked, how would you go about doing this? Well, what we can say is this. Log 10, replace d with 1. 1 plus 1 over 1. We're looking for log 2. Put log 2 into your calculator. 30. Yeah? The next one is start with 2. It's going to be 1 plus a half, which is 3 over 2. So then you're going to put in log 10 3 over 2, or log 3 over 2. And there's your 18%. And then finally, a ninth is going to be 1 plus 1 over 9, which is going to be, we can just do 1 and 1/9 if we want. We don't have to necessarily do just a button for that. Shift this button here. What's a 1 and 1/9, is it? And then what we get here, 0.475 or 5%. Alright. It's 16. Number of bacteria in a particular culture is discovered to be 40 by 25 plus e to the t over 50. Okay, number of bacteria, so I'll call this n of t if I want to call it that. State the number of bacteria at the start of the experiment. When the experiment starts, t equals 0. So it's going to be 25 plus, oh sorry, I've got the 40. It's going to be 40 multiplied by 25, and what's e to the power of 0? 1. 40 by 26, which is 1040 bacteria. Calculate the time it takes for the bacteria to reach 1200. Give your answer to the nearest tenth of a day. What does n of t represent? Number of bacteria. 1200 equals 40, 25, e to the t over 50. Divide by 40, we get 30. 30 equals 25 e to the t over 50. I brought down the 40 underneath. Bring over to 25. 5 equals e to the t over 50. How did you get rid of a t in the power position? ln both sides. And then what do we do next?
Bring down the power.
Bring down the power. ln e is 1. No good. Equals ln 5. Bring up the 50 ln 5. Anybody in the calculator?
Race.
80.47 or 80.5 days.